Okay, today we're going to talk about rational functions. What does rational numbers mean?
It can be written in a fraction.
Yeah, it can be written as a fraction. You guys are so good. Okay, so we're going to be graphing functions that are in fraction form. We have x in the denominator at the very least, and possibly more than likely in the numerator. Okay, so first thing we're going to talk about is vertical asymptotes and how to find them, and we've already talked about this here. But first thing you want to do is factor numerator and denominator. So that was pretty easy to factor. What do you notice? You can cancel x plus 2. So when you cancel a factor from the when you can cancel a factor, remember x still cannot equal negative 2. So when x equals negative 2, it creates a hole in the graph. This is not a vertical asymptote. It creates a hole in the graph. So if I continue simplifying this, after I cancel it, it simplifies to 1 over x minus 2. So the hole is going to be at negative 2, comma. If I put negative 2 in this simplified function, it would put me at negative 1 over 4. Okay? That's where the hole would exist. So if you have a factor that cancels, that x value from the denominator creates a hole. All right. The x value that does not cancel, that factor, he gives you the vertical asymptote. All right. So we are going to show you real quick why you need to understand this and not rely on that lovely graphing calculator that you love so much. She's like, it will do everything for me. Oh, I just tried that. Keep this up here. Okay, ready? Here we go. This is our graph. You can ignore the red one. I gotta take it off. I can't do it. All right. So look at this. Do you see the hole? You don't see the hole. Don't lie to me. Where's the hole? You see a hole in the graph?
I see a lot of empty space.
You do see
In the middle of it.
Okay. So let's look real quick at this. This empty space that you're thinking of is the what? This is the asymptote. That's the asymptote at 2. You see the hole in the graph, though. There's a hole in that graph. You have to zoom in. So if you don't know it's there, are you going to see it? No. So look here. If I go to the window, and let's say I just want to look from negative 3 to negative 1, and I'm going to zero in on that. It's going to look right real close. Watch. You see the hole?
Oh, I see the hole. Now I see
It looks like a missing pixel.
It just like stops.
It just jumps. It hops over that point. X cannot equal negative 2, people. So it's got to hop over it. But the function that's graphing, this function, if we just looked at it without the hole, it would be 1 over x minus 2. Remember that 1 over x reciprocal function that we talked about, parent function, that got shifted over to? But this one has a hole in it because we canceled a factor. Okay, so if you don't know the hole's there, you're not going to be able to graph and go, yep, I know there's a hole.
So do we have to know, like, are we going to ever have a question where it's like, know the domain, and then we just flip it?
Mm-hmm. So if I wanted to write the domain of this guy, and you can do the domain just from the denominator, right? The domain of this graph starts at negative infinity, goes to negative 2, jumps over negative 2, goes to 2, jumps over 2, goes to infinity. So the domain issue is still there, just like we did at the beginning of the year. But this just happens to be a hole, and that happens to be an asymptote. Okay, so we're getting more into specifically what those are when we have a domain problem. All right? So, let's try the next guy. See how we do. Any questions on what we did so far? So, first thing we're going to do is factor. Again, if you can't factor this quickly, it makes your life horrible in here. You know what I mean? You are not a good place. All right, so we practiced it. Do we have a hole in this graph?
No.
No holes. Nothing cancels. Yeah. So what are the vertical asymptotes? -5 and 2. Notice I wrote x equals -5 and 2. If you do not write x equals, I'm going to take a point off. Every time you do not write x equals. It is a line. It's a vertical, invisible boundary line. There's another one coming in. Look.
Is this on? Yeah.
That's fine. One person in a million is going to listen.
That was Friday, October 4th.
October 4th. Very cloudy day, but I see some blue. All right, moving on. Horizontal asymptotes. Easy. I think we kind of already talked about this a little bit. Maybe not. You have 3 scenarios here. When you look at the degree in the numerator and the degree of the denominator, if the numerator's degree is smaller than the denominator's degree, you have a horizontal asymptote at 0 every single time. So if I have a square on the top and a cube on the bottom, y equals 0 is the horizontal asymptote. If the degrees match, if they're the same, I have a cube on the top and a cube on the bottom, I'm going to look at the coefficients, the leading coefficients, top and bottom. That's my horizontal asymptote. If the degree on the top is bigger than the bottom, there's no horizontal asymptote. That creates what's called an oblique asymptote. Okay? So, this is what an oblique looks like, just so you're aware. I want to keep up here. See how this exponent's bigger than this exponent?
Yeah.
Okay. So it doesn't level off horizontally, but you can see it shoots off. This is the oblique asymptote. If I were going to look at this, you would have an asymptote here. You see that? It guides how the graph goes off the page. Okay? So that's an oblique asymptote. I don't know if you went into those last year at all or not. Yes, no?
I don't think so.
I don't know. I blocked it out. Okay, let's look at these examples. We are only looking at the leading term. Remember, leading term means term with the highest exponent. It doesn't always mean one in front. Sometimes they're not written in standard form. So look at the exponents. Which situation do we have? They are the same. So we're now just going to look at the coefficients, which is 2 over 3. Done. That is the Y-intercept, or horizontal asymptote. Easy breezy, right? Next one, we have an x squared over an x. So, do we have a horizontal asymptote? No, it's oblique. It's oblique. Meaning it's tilted. It's a tilted line, not a horizontal line. Okay, last one. We have in a 1 power and a square power.
Y equals 0.
Y equals 0. Understand, if you do not remember the rules, I can't remember anything. Put in 1,000 for the x. Okay? What are you talking about, Mrs. Tavarchuk? Let's look. Let's say I can't remember the bottom one. If I put 1,000 in, and I divide it by 1,000 squared, you see how it's getting close to 0? Okay. If you go to the top one, 2 times 1,000 divided by 3 times 1,000. I know I can multiply it in my head, but I'm not. Ooh. Okay, so you can see. All right, here we go. Bing. Fill in the blanks. What are the vertical asymptotes of this graph? Okay, 3 and negative 3. All right, we are doing asymptotic behavior. What is the graph doing as it approaches those asymptotes? Understand, a vertical asymptote cannot be crossed. So imagine a spaceship, if you will, flying towards the asymptote. It has to, it's either going to shoot up or shoot down, right? Only choice, you cannot go through. Like Star Wars. So when you are talking about the behavior towards an asymptote, you're saying, is the spaceship going up or is he going down? So on this one, do you see x is approaching negative 3, and do you see a little negative? You can't see it on the board. Do you see a negative on your paper?
Yeah.
So that means negative 3 on the left. Where did the rocket ship go? Did it go up or down? It went up, so we are going to infinity.
But how do we know it's going?
Okay, well look.
Oh. Oh.
Now if the rocket ship is going the same line but coming from the other way, here's my rocket ship, where did it go? It went down. So on the positive side of negative 3, it's going down. How about this guy over here? On the left side of that asymptote, where did the rocket ship go? Up.
Down.
Down, right? And on the right side, it went up. Now, are those always opposites? No. So you just have to look. You're looking on the left side of the vertical line and the right side. Where's the rocket ship? Is it below or is it above? Horizontal asymptotes. What do we got here? Y equals 2. Just 2, right? Oh. On the graph, kids. No calculations necessary. All right, now we're going to talk about in behavior. So in behavior means as x gets to the left of the graph, clear on this side, is it leveling off somewhere? Yeah, at that asymptote, right? If there's a horizontal asymptote in a rational function, it is going to be the in behavior on both sides. Automatic. So these are both 2. But you can look at the graph. You see how the rocket ship is sliding along that graph? That line? It's never going to cross it. It's got to skate on it. Okay? Now, you're going to, domain and range. What's my domain? Furthest left it goes is? And it jumps at negative 3. 3, and then it jumps 3 to infinity. Very good. What's the range? Negative infinity to where?
Oh, to 0. No, it's 2. 3 seconds.
To 2/9. See how this little parabola guy turns around at 2/9? The y is 2/9. And it includes 2/9. This is kind of different. Then it jumps.
Oh, 2/9.
No, there's nothing between 2/9 and this asymptote. So we are jumping, now we're going to go above 2, and it keeps going up. Okay, does that make sense? All right, here we go. Now, when I ask you to find in behaviors or limits, you must write them in this form, and you can spread them out on your paper a little bit. I know they're kind of crammed in. I changed mine a little bit after I copied it. So how would what is x approaching when you go to the little blue-red planet? What is x approaching? Negative infinity, right? You're going to the left side of the graph. So as x approaches negative infinity, what is the height leveling off at? What's this height?
It's going to be infinity. Or the height.
The height.
It's going to reach 0.
It's going to, yeah, it looks like it's going to touch 0. It never does. That's an asymptote. Okay? Let's go to the star. The star is next to a vertical asymptote, yes? So what is x approaching at the star? The x. -2. Wait. I'm just talking about the x. The x is approaching -2 from which side? I'm sorry, -1 from which side? From the left. Where's the rocket ship? On the star side there. The rocket ship's going
Infinity.
up. Yep. We're looking at the flower now. On the bottom there. So where is x approaching? -1 from the right side. Now where's the rocket ship? Down, -infinity. So you've got to get the x value placed as well, not just the answer. My little orangey yellow planet. What's the asymptote that we're going to there? 1, and the orange planet is on the left side. That should really be kind of moved over maybe to here. Okay, so it's approaching 1 from the left. And where's my rocket ship? Infinity. My little twinkle stars you can't really see. My little twinkle stars are approaching 1 from the right side. And where's my rocket ship? -infinity. Where is that little twinkly guy? And the smiley face is an end behavior. As x approaches positive infinity, it's leveling off to 0. My end behavior should be the same. As x goes to -infinity and positive infinity, if there's a horizontal asymptote, they should both be the same. All right, what's our domain? -infinity to -1, jump. -1 to jump. 1 to, very good. What is our range? Lowest it goes is? Now look at the middle. You see how there's no breaks. It goes all the way up to positive infinity. It is possible to cross a horizontal asymptote inside. At the end, it won't cross. Inside, it can cross. Horizontal asymptotes. Verticals, never, ever, ever. Okay, let's list, what are the vertical asymptotes? We've already wrote them. -1 and 1. Horizontal is at 0. Okay. I understand how to write those. All right. Graphing rational functions. So I added a couple things to this. The first, or the 0 step, whatever, you should factor the numerator and denominator. We need to have those factors to check for holes and asymptotes and all sorts of stuff. So factor the numerator and denominator. Figure out if you have any holes first, just like we did with that first example. It doesn't matter, 2, 3, or 4, which ones you want to do first. It doesn't matter. You can switch them up. And then 5 is you're going to have to use some test points to figure out the graph. And then we're going to sketch it. So let's look. This is already factored for us sometime. What do you notice? It will reduce to what? X over x squared minus 9, because my x minus 1 is going to cancel, which means what? We have a hole. X equals 1 is going to give us a hole. And where is that hole going to be? I know the x's part is 1. If I put it up into this function, 1 over 1 squared minus 9. That gives me my y part of the hole. See that? So I can graph that. I'm over 1, down 1/8. There's where my hole is. Okay. Let's go further and say x squared minus 9 equals 0. So we are finding the vertical asymptotes. The vertical asymptotes are when the denominator is 0. So x squared equals 9. X is going to equal what? Plus or minus 3. Make sure you do the plus or minus. Vertical asymptotes, we got, what's the horizontal asymptote? Look at the reduced function. What do we got? Zero. Okay. X and Y-intercepts. X-intercept is when the function equals 0. When does a fraction equal 0? When the numerator is 0. So you're only going to set the top equal to 0. So I'm going to say x-intercept is when x equals 0. You can't do anything with it. It's already solved. That's my x-intercept. My y-intercept is when x equals 0. So in my function, if I put 0 in for x, I'm still getting 0. Remember, you can't have an x-intercept of 0 and not have a y-intercept of 0. All right, there's our graph. Do we need a few more points to figure out where things are? Maybe, okay? So we need to figure out where our rocket ships are going. So we have an end behavior of 0, but understand, that means I can be coming along this and hit and go up, or along it and hit and go down. We have to figure out which one it is. So we need to pick a number close to the asymptote on the left side. What number do I want to put in? 4. 4? Okay, so I'm going to make a little t-chart. And I'm going to put in -4. So in this simplified function, if I put in -4 for the x, I get -4 on the top, and on the bottom I would have 16 minus 9, which would be 7. That is a negative number, which tells me the branch is in the negative region, below that horizontal asymptote at 0. I don't need to get any more detailed than that. Okay? I need to figure out on the other side, where is my spaceship? So instead of -4, I'm going to put in -2. I'm going on the other side, the right side of -3. So I have -2 over 4 minus 9 is -5. What does -2 over -5 mean? Positive, right? Again, I'm going to be up here. So I have to come down. Guys, I have to sneak over here and grab these 2 points. I have to come over and grab the 2 points. It's not going to go up and down, up and down, up and down inside here. It's going to come down an asymptote. It's going to go over and either continue going down or go back up. So we know we grab these 2 points. What can I plug in to find if it goes up or is it going to go back down? 2. Put 2 in there. I get 2 over -5, right? So that is negative. That means I'm going to continue and go down that asymptote. So I saw that little hole. And then I'm going to put in last number. 4. 4 over 7 is positive. So that tells me my last branch is going to come down in the positive area over there. Does that make sense? You've got to figure out, am I below the asymptote or above the asymptote on the ends? And then, where's my rocket ship? one more, and we're done. So we are going to factor the denominator. So I get 2x, x, 3, and a 1. Can you factor the numerator? No, not with rational coefficients. So, can I cancel anything? No, so there's no holes. So start right now at vertical asymptotes. What do we got? Set these guys equal to 0. X equals 1 and -3/2. Okay. Horizontal asymptotes. Look at the original function. Compare the y equals, remember it's the coefficients, 2/2 is a 1. Okay. X-intercepts. We're going to take the numerator and set it equal to 0. So we get x squared equals 1/2. Remember, that's plus or minus 1 over the square root of 2. We can't leave it like that. We're going to rationalize that denominator and multiply by the square root of 2 over the square root of 2. Okay. That is approximately 0.71. So we can sketch those x-intercepts. Okay. We good? And the last thing we're going to do is the y-intercept. Look at the original. What is the constant on the top and the constant on the bottom? -1 over -3. That's your y-intercept. I can pretty much see what's happening in between these asymptotes, can't you? You can tell it's going to come up and go back down. So inside, we're good. Okay. We need to get the left and the right sides here. So what number am I going to put in for the left? Can I do -2? That's -1.5. Into the original, -2, I get 8. -1 is 7 up top. And on the bottom, it's 8. -2, -3. So I have 7 over 3. That's positive, right? Ah! Do we really care if it's positive or negative, or is it above 1? Because asymptote's at 1. So, but it's still above 1. So we're going to come along here and shoot it up. Okay. If I put in 2, I get 7 over 7, which equals 1. That doesn't tell me anything. So go closer to the asymptote. Let's put in 1.5, and you can use your calculators. Figure this out. Put it in the original function. The top is 3.5. .5 over 3, which is bigger than 1. So we're above. Does that make sense?